Alright, let's go. Number 10. The Deep Field Data Debate. In the mid-2010s, Nyayesh Afshordi at the Perimeter Institute was working with a team testing whether cosmic microwave background data could distinguish between standard inflationary cosmology and a radically different alternative, a holographic model of the early universe with no inflation at all. Standard inflation predicts specific statistical patterns in the CM's temperature fluctuations, patterns matched extensively by the MAP and Planck satellites over 2 decades of observation. When Afshordi's team ran a non-inflationary holographic toy model instead, a quantum field theory living on a lower dimensional boundary, with no extra spatial dimensions required. It fit the data just as well. Afshordi, along with Claudio Corian, Luigi Del Rose, Elizabeth Gould, and Kostas Skenderis, published the result in Physical Review Letters in 2017. Their holographic model matched DoMap's angular power spectrum data across the full range they tested, statistically indistinguishable from the standard model's predictions. Critics pointed out the holographic model still required boundary parameters tuned by hand, not derived from first principles. Others called it a degeneracy problem, 2 totally different physical descriptions producing identical observable signatures, which isn't evidence for holography so much as a limit on what the CMB can rule out. A handful of cosmologists went further, arguing the entire comparison was cherry-picked, since the holographic toy model hadn't yet been tested against the more recent, higher-resolution Planck satellite data at the time of publication. If both pictures fit everything we've measured of the sky, then the question of whether the universe is holographic may not be answerable with the data we currently have. What if 2 irreconcilable pictures of how everything began look, from where we're standing, exactly the same? Nobody has closed that door. Number 9. The Planck-Scale pixelation problem. In 1993, Dutch physicist Gerard 't Hooft was wrestling with a foundational mismatch between general relativity's smooth spacetime and quantum mechanics' discrete rules at the smallest scales. Conventional field theory assumes the number of independent physical degrees of freedom inside any volume of space scales with that volume. More space, more room for information. But when Hooft tried to count the degrees of freedom actually permitted by black hole thermodynamics, the volume scaling rule broke down completely. Information scaled with surface area instead. In his 1993 paper, Dimensional Reduction in Quantum Gravity, presented at the Solemnfest conference, 't Hooft proposed that any region of space can be fully described by degrees of freedom living on its boundary. 1 bit per Planck area, roughly 2.6 times 10 to the power of negative 70 square meters. Physicists spent years trying to build concrete models where this pixelation would show up in ordinary experiments. None succeeded at accessible energies. The Planck scale sits beyond what any particle accelerator, including the Large Hadron Collider, can probe by roughly 15 orders of magnitude. Leonard Susskind extended the idea in his 1995 paper The World as a Hologram, published in the Journal of Mathematical Physics, but even he acknowledged the mechanism connecting the deep math to observable pixels remained unclear. Susskind himself noted that the bound had been derived from black hole physics specifically, and generalizing it to all of space, including the empty room around you, was an extrapolation nobody had proven rigorously. If 't Hooft is right, the smooth space you're sitting in isn't smooth at all. It's a coarse approximation of something finite and granular, the way a photograph looks continuous until you get close enough to see the dots. If space is made of a finite number of pixels, what determines their number, and what exactly is doing the counting? A different set of scientists thought they'd actually heard it. Number 8. The GEO600 anomaly. In the mid-2000s, the GEO600 gravitational wave detector team in Hanover, Germany, was working through a routine calibration problem, an unexplained noise floor limiting the machine's sensitivity. Standard interferometer noise models assign a source to every hump in the spectrum: thermal vibration, seismic activity, laser shot noise, all identifiable, all subtractable. GEO600's noise refused to match any known source, and stayed stubbornly present across the mid-frequency range no matter what the team isolated or removed. Fermilab physicist Craig Hogan contacted the GEO600 team in 2008, having predicted, before ever seeing their data, that a holographic noise signature from Planck-Scale spacetime fluctuations should appear in exactly this kind of interferometer. At exactly this magnitude, as a sideways jitter in the beam splitter's position. The GEO600 team tested the prediction by shifting the detector's frequency response, since holographic noise should behave differently than a gravitational wave signal. Independent theorists, including a 2009 reanalysis by Richard Liu and Lloyd Hillman at the University of Alabama in Huntsville, disputed core parts of Hogan's derivation, arguing the predicted noise level was off by orders of magnitude once the interferometer's actual light travel geometry was accounted for properly. Other groups suggested the noise might trace back to unaccounted for scattered light inside the vacuum system, a mundane engineering explanation the GEO600 team never fully confirmed or ruled out. Nobody produced an alternate explanation that stuck. Either, the anomaly, quietly, is still unexplained. If Hogan's interpretation holds, a machine built to catch ripples from colliding black holes may have accidentally recorded the fundamental graininess of the fabric you're moving through right now. No one working on GEO600 will confirm the noise is holographic. No one has explained what else it could be. The idea didn't start with an experiment, though. It started with a paradox. Number 7. The Bekenstein bound. In the mid-1970s, Jacob Bekenstein at Princeton was working on a problem that threatened the second law of thermodynamics itself. What happens to the entropy of matter that falls into a black hole and disappears behind the event horizon? Thermodynamics says entropy, a measure of hidden information, can never decrease in a closed system. If matter carrying entropy vanishes with no way out, the total entropy of the universe would appear to drop. Bekenstein resolved it by proposing black holes carry entropy of their own, but the formula he derived didn't scale with volume. It scaled with the area of the event horizon. Bekenstein published the initial result in Physical Review D in 1973, then generalized it into a universal bound in a 1981 paper in the same journal. The maximum entropy any bounded system can contain is proportional to its surface area divided by the Planck area, not the volume it occupies. Stephen Hawking's 1975 derivation of black hole radiation confirmed the entropy formula rigorously, forcing the field to take the area scaling seriously as fact, at least for black holes. Other theorists tried to find loopholes, proposing thought experiments involving systems with unusual shapes or exotic matter that might exceed the bound, and each attempt, when worked through carefully, ran into the same wall. Violating the bound seemed to require also violating causality itself. It took nearly 2 more decades, through Hooft and Susskind, for anyone to seriously propose the bound might describe every region of space, not just black holes. If the Bekenstein bound applies generally, the maximum information that could ever describe you, every memory, every cell, every thought you've had, is capped not by how much space your body occupies, but by the surface area of the skin containing it. Why would information care about a surface instead of the space it fills? Eventually, someone tried to test that directly, with a machine built for exactly this purpose. Number 6. The Fermilab Holometer. In 2009, Craig Hogan proposed a dedicated experiment to test his holographic noise prediction directly, rather than lean on an ambiguous signal borrowed from a detector never built for the purpose. Standard physics predicts ordinary quantum gravity fluctuations are far too small, by many orders of magnitude, for any interferometer humanity could build to detect. Hogan argued that if the holographic principle were true, the predicted fluctuations would be dramatically larger, sitting right at the edge of what current interferometer technology could measure. The holometer, officially Fermilab Experiment E990, ran 2 overlapping 40-meter Michelson interferometers from 2014 through 2016, publishing results in Physical Review letters. Hunting for correlated noise at a spectral density set entirely by the Planck time, roughly 5.4 times 10 to the power of negative 44 seconds, with no free parameters to adjust. The holometer found nothing. No correlated holographic noise above the baseline. Hogan didn't abandon the underlying theory. He proposed the signature might instead appear as space-like rotational correlations. tested in a follow-up bent arm configuration published in 2020, which also came back empty. Physicist Sabine Hossenfelder argued publicly the entire program had been chasing a poorly motivated model from the start, calling the eventual null result unsurprising given how speculative the original theoretical basis was. Hogan disagreed, telling Symmetry magazine after the results were published that the holometer had still developed an entirely new way of studying space and time, one that hadn't existed before his team built the machine. Ruling out Hogan's specific model doesn't rule out the holographic principle itself. It just means if space really is pixelated, the grain size, or the way it reveals itself, isn't what two of the most sensitive interferometers ever built expected to find. If the most direct search for spacetime's graininess came back silent, does that mean it isn't there? Or that we're still asking the wrong question? The deepest version of this problem was never about noise at all. It was about what happens when something falls in and never comes back. Number 5. The black hole information paradox. In 2019, a group of theorists including Ahmed Almheri, Netta Engelhardt, Donald Marolf, and Henry Maxfield returned to the black hole information paradox, a problem Stephen Hawking first raised in 1976 and never fully solved. Hawking's calculation showed radiation escaping an evaporating black hole comes out perfectly random, carrying no information about what fell in, implying information, and the deterministic core of quantum mechanics with it is genuinely destroyed at the event horizon. Using a technique borrowed from ADS/CFT, the team found that past a certain point in a black hole's evaporation, an island of interior spacetime becomes information theoretically counted as part of the boundary's data, letting outgoing radiation reconstruct what fell in after all. Almheri, Engelhardt, Marolf, and Maxfield published the result in 2019, followed within months by an independent paper from Jeff Pennington, both showing the black hole's entropy tracks the Page curve, a prediction Don Page made back in 1993, exactly, once the island contributions are included. For over 40 years, every proposed fix, from remnants to firewalls, had violated either quantum mechanics or general relativity. Hawking himself only conceded the paradox in 2004, losing a public bet to Kip Thorne and John Preskill, without offering a full resolution. The island calculation is the first to reproduce the expected curve, but it relies on a mathematical procedure called the replica trick, borrowed from statistical mechanics, whose physical meaning inside an evaporating black hole nobody can fully explain, even the physicists who use it correctly every day. If information really is preserved by encoding a black hole's interior onto its boundary, the same principle applies to you. Your body's information may, in some description nobody fully understands yet, exist duplicated on a surface you will never see. Where, physically, is that boundary supposed to be, and were you ever really only in one place? To understand why any of this was even mathematically possible, you have to go back to the moment someone proved it outright. Number 4. The ADS/CFT Correspondence. After Juan Maldaceno's 1997 conjecture, Edward Witten at the Institute for Advanced Study, and separately Stephen Gubser, Igor Klebanov, and Alexander Polyakov set out to work out the precise dictionary translating between the two sides of the proposed duality. String theory calculations involving gravity in a 5-dimensional curved space were notoriously difficult, often impossible, to solve directly. Witten and Gubser, Klebanov, and Polyakov showed that specific gravitational calculations in the 5-dimensional bulk translated exactly into ordinary, non-gravitational quantum field theory calculations on its 4-dimensional boundary, no gravity required on that side at all. Witten's paper, Anti-de Sitter Space and Holography, and the Gubser-Klebanov-Polyakov paper. Gauge theory correlators from non-critical string theory both appeared in 1998, turning Maldaceno's conjecture into a working computational tool now cited in more than 20,000 subsequent papers. Skeptics noted the duality had only been rigorously demonstrated in an anti-de Sitter universe with a negative cosmological constant, the opposite geometry from our own, which is expanding, with an apparently positive cosmological constant. Attempts to build an equivalent DS-CFT correspondence for a universe like ours, including work by Andrew Strominger in 2001, produced far weaker, more contested results. Strominger's DS/CFT proposal ran into a basic technical obstacle. Unlike anti-de Sitter space, de Sitter space has no true time-like boundary at infinity where a well-defined dual theory could sit. Only a boundary in the infinite future, after everything measurable has already happened. The duality's most spectacular success remains, formally, a description of a universe we don't live in. If it applies to our actual reality, gravity, the force keeping your feet on the floor right now, isn't fundamental at all, but a mathematical illusion generated by information encoded somewhere you can't access. If gravity isn't fundamental in the mathematics that works, why does it feel so real to fall? The man who started it wasn't looking for any of this. He was just trying to finish a calculation. Number 3. Maldaceno's discovery. In 1997, Juan Maldacena, then a young researcher at the Institute for Advanced Study, was studying D-branes, extended objects in string theory, working out their low-energy physics from two completely different angles. One angle, treating the branes as sources of gravity, produced a supergravity solution in a 5-dimensional anti-de Sitter geometry. The other, treating them as boundaries where open strings end, produced an ordinary 4-dimensional quantum gauge theory with no gravity at all. Standard practice treated these as two separate approximate descriptions, useful in different limits. Maldacena realized they weren't approximations of each other. They were exactly, precisely the same theory, described from a different number of dimensions. Maldacena submitted the paper in November 1997. It was eventually published in the International Journal of Theoretical Physics, and by its 25th anniversary in 2022, had become, by most citation counts, the single most cited paper in the history of theoretical physics, with more than 20,000 citations. Physicists initially treated the correspondence as a useful trick specific to string theory's math, not a statement about physical reality. It took years of cross-checks, matching correlation functions, black hole entropies, and thermal properties on both sides, before the field accepted the duality wasn't a coincidence of the equations, but something closer to two languages describing one identical object. Even now, no one has produced a full, non-perturbative proof of the conjecture from first principles. Every confirmation, however extensive, remains a case-by-case demonstration rather than a general theorem. If Maldacena's duality reflects something true about physics in general, the three spatial dimensions you experience, up, down, and sideways, might be exactly as derivative, exactly as emergent, as a hologram projected off a flat card. If a lower dimensional surface can fully describe your three-dimensional world, which one of them is the real one? Somebody eventually asked a more uncomfortable question: what if gravity itself is just a side effect? Number 2. Emergent gravity. In 2009, Erik Verlinde at the University of Amsterdam was working on the long-standing puzzle of why gravity, alone among the four fundamental forces, had resisted every attempt at reconciliation with quantum mechanics. Standard physics treats gravity as fundamental, carried in most frameworks by an undetected particle called the graviton, on equal footing with electromagnetism and the nuclear forces. Verlinde proposed gravity isn't fundamental at all, that it emerges as an entropic force, a statistical effect, like gas pressure, arising from how information is organized on holographic screens surrounding matter. Verlinde submitted On the Origin of Gravity and the Laws of Newton to ArXiv in January 2010. It was published in the Journal of High Energy Physics in April 2011. From a purely thermodynamic argument, using the holographic principle and the Unruh temperature relation, he derived Newton's law of gravitation, and, in a relativistic extension, Einstein's field equations themselves. The paper drew rapid, detailed criticism. Sabine Hossenfelder published a rebuttal the same year, questioning the internal consistency of treating gravity as purely entropic. Archul Kobakidze published a 2011 paper in Physical Review D, arguing entropic gravity was directly contradicted by existing neutron interferometry experiments sensitive enough to detect any deviation. Verlinde revised the framework through the 2010s, extending it in 2016 to explain galactic rotation curves without dark matter, a claim that remains independently disputed, since it has not yet produced the same precision fits to cluster-scale gravitational lensing data that the standard dark matter model achieves. If gravity really is emergent rather than fundamental, then every object that has ever fallen toward you, and every time gravity has held you to the Earth, was never a force at all. Just entropy quietly doing its accounting. If gravity is just information rearranging itself, what is doing the arranging? And why does it look so consistent? The final entry doesn't ask whether space is a hologram. It asks who's protecting it from being erased. Number 1. Spacetime as a quantum error-correcting code. In 2014, Ahmed Almheri, Shi Dong, and Daniel Harlow, working across Princeton and MIT, were trying to understand a strange redundancy in the ADS CF dictionary. The same point deep inside the bulk space seemed reconstructible from multiple, different, non-overlapping regions of the boundary theory. In ordinary physics, if you destroy the specific patch of data describing an object, that information is simply gone. There's no backup written elsewhere by default. The team recognized this redundancy wasn't a coincidence. It was structurally identical to quantum error correction, the mathematics engineers use to protect quantum information from being lost when part of a system is damaged or measured. Almheri, Dong, and Harlow published bulk locality and quantum error correction in ADS/CFT in the Journal of High Energy Physics in 2015. The same year, Fernando Postowski, Benny Yoshida, Harlow, and John Preskill built an explicit toy model, the Happy Code, in the same journal, using pentagon-shaped tensor networks to demonstrate the mechanism concretely. Some theorists questioned whether these discrete tensor network models actually captured the continuous geometry of real spacetime, or were just a suggestive analogy. Others pointed out that the specific relationship required between logical and physical information has never been derived from string theory's fundamental equations. It was reverse engineered to fit, not predicted in advance. Daniel Harlow himself, in a 2017 follow-up paper connecting the error correction picture directly to the Ryu-Takeyanagi entropy formula, acknowledged the framework still describes toy models built from discrete networks of qubits, not the smooth, continuous spacetime physicists actually need to explain. If spacetime genuinely is a quantum error-correcting code, then the space around you, and the fact that you don't blink out of existence when a stray photon disturbs a few atoms, isn't a property of the void. It's protection, actively encoded, the same way a hard drive is engineered not to lose your files. If spacetime is a code correcting for errors, what exactly counts as an error? And who wrote the correction into place? None of these 10 entries sit at the edges of what physics knows. They sit at the center of it, inside black hole thermodynamics, inside the equations that already won Nobel Prizes, inside the tools theorists use every day, without controversy. The universe isn't confused about what it is. We're the ones still arguing over whether the floor beneath us is fundamental, or just very good bookkeeping. Every one of these results survived peer review. None of them agree on what reality is actually made of. If you want to see more videos like this, click the video on screen now.